Wow. Now we know who will be taking the extra credit part of the exam. Okay. Next lecture is Neill.
So this doesn't count for any exam. This is where we wander massively off the reservation because I work in galactic structure and not on stellar associations. But I think there are things in here that are relevant. There are things in here which, if you think about what you know about associations and how they evolve, that are relevant to the bigger picture. And as it says in the next slide, globulars are clusters too. And once they were young. So that's what I'm going to talk about here, about the halo. And the other reason why I'm talking about it is because I think this year is an important 50th anniversary for a paper, one of those fundamental papers that if you haven't read, you should read. And we'll have a little quiz on that a little later. Okay, so globular clusters. They're the most prominent members of the halo population within the galaxy. They're also visible in, and actually I know there are some people here who work in globulars, so well done you guys. They're also prominent around other galaxies, spirals and ellipticals. There's 147 clusters currently known within the Milky Way. They're concentrated towards the galactic bulge, and they were a key part in Shapley determining how big the galaxy was, at least where the center of rotation of the galaxy was, since looking at the globular clusters and figuring out, based on the anomalies, the variable stars there, roughly what the distance was, he could see that it was much, much bigger than people had thought up to now. The total population, allowing for obscured systems, I mean, there may still be some that are hiding here in the disk of the Milky Way, is estimated at around about 160. The total mass in globular clusters is pretty small. It's about 10 to the 7 solar masses in total, and that's estimated as 1 to 2% of the mass of the current halo. That's going to come in later when we talk about how thinking has evolved in the role that globular clusters played in the evolution of the galactic halo, the formation of the galactic halo. But in any case, the current systems are clearly a remnant population from the first major outburst of star formation within the Milky Way. So their properties, this is all, a lot of this is taken from, I was going to say Hugh Harris, it's not Hugh Harris, but William Harris's review articles. Some of them are moderately out of date, but the cluster metallicity distribution, this is solar, this is going down to 10 to the minus 2. There's a kind of bimodal distribution in metallicity, a broad distribution in metallicity going back down to much less than 100th the metallicity of the Sun. The globular cluster population are alpha enhanced. That means that they must have formed rapidly before there were significant numbers of type 1a supernovae to pollute or to add extra iron into the ISM. So again, this is saying that they formed, like the halo stars, they formed early on in the life of the galaxy. And these two plots here are just the distribution in X against Z, Y against Z and X against Z, the three-dimensional distribution of them relative to the galaxy, and they're pretty much concentrated towards the galactic center. The overall distribution goes as roughly a power law of r to the minus 3.5, where r is the radial distance from the center of the galaxy. In terms of their kinematics, and maybe I can amplify on something I said yesterday, they're what I would call a pressure-supported system. Now I see things in two ways. There's two, you want to support a system against gravitational collapse. This holds for clusters as well as for galaxies. There's two ways of supporting that system. Actually, it holds for accretion disks as well. You can either have something that rotates, which is systematic motion in one direction, or you can have something that's supported by random motions, which I would call pressure supported. And I was thinking that dichotomy actually probably goes back to Cormody's lectures 30 years ago at Saas-Fee. But the halo is a pressure supported system, and I guess when I was talking, I may not have explained the asymmetric drift yesterday with regard to stars in the solar neighborhood. It's asymmetric because the mean motion is always heading towards greater lag in rotation velocity. And as you get greater lag in rotation velocity, you get greater velocity dispersion. So as a simple way of thinking of that is you've got constant energy. And as you transfer energy from rotation to velocity dispersion, you're transferring it from rotation to pressure support, then you have to slow down your mean rotation because you're giving it to the pressure I don't know if that's the right way of thinking about it, but it seems to make sense to me. Anyway, moving on. Field halo stars. They're rare locally. About 1 in 200 of the local stars is a member of the galactic halo. They have a similar density distribution to the globular clusters. With the halo stars, there's more of them. So you can actually see that around about 70 kiloparsecs, it looks like there's a cutoff, that the density distribution changes. It's r to the minus 3, but when 3 and 3.5. What's that between friends? And again, they have large negative v, means that they're not rotating, and they have a large velocity dispersion. So this is from Carney's survey of subdwarfs, I think probably the same survey that Bob referred to yesterday. And they have similar abundances. They're alpha enhanced on the whole relative to disk stars. I'm not going to get into this, but there is some suggestion that the halo itself might be complex and that there are two different populations in there. But that's a detail that even I'm not going to burden you with in this series. So what's the anniversary? Well, Egan, Lindenbell, and Sandage. How many here have heard of that paper? How many here have read it? Well done, you guys. The rest of you should read it, because there are some papers that are so important that regardless of how things have moved on, and things actually may not have moved on as much as you might think, you should read them because they changed the way that we thought about things. This was the first paper that really tried to put together a model of how you build the Milky Way galaxy. And there are things in that paper. This is Egan, Olin Egan, Donald Lindenbell, Alan Sandage, the three musketeers. There are things in that paper that come through later on and affect clusters. For example, there's the seeds of violent relaxation, I think, are in that paper. So it's well worth reading.
Kathy and I were noticing yesterday that the seeds of that paper were in Spitzer and Schwarzschild.
Yes, that's true. That actually is the idea of a collapsing structure, which is what this builds on and quantifies, was in the Spitzer and Schwarzschild. So the idea was obviously bouncing around. So I'm going to have a big historical diversion now, because I think it's interesting. Just this is 50 years ago, but the whole zeitgeist of how you thought about the galaxy and how you thought about the local solar neighborhood and what you thought about the universe, it really has changed radically since then. And it's quite remarkable to think how that has happened. So on the largest scales, George Gamow had proposed his Big Bang model, and it was called the Big Bang model because of something Fred Hoyle said in a BBC radio lecture, which Fred afterward claimed was not derogatory, but since he was pushing his steady state theory at the time, it may have been a slightly derogatory term to it. But it's one of these things when you give something a name, that name takes on a life of its own, and you can't stop it being named that. So the Big Bang theory is what Gamow's model became known as. The microwave background hadn't been detected yet. Bada had resolved about, this was the ELS paper was 62, so almost 20 years before that, Bada had actually resolved the M32, a satellite of M31, into stars, and recognized that the bulge of M31 was in a similar situation. So he talks about two stellar populations there. This is the diagram from his 1944 paper. Population 1, which goes all the way up to O and B stars. So population 1 is what you love, and then population 2, going over here, was an evolved giant branch star, an older population. Globular clusters. Alan Sandage and Halton Arp were working on the first set of deep photometry of globular clusters in the early 1950s. This is the first really detailed color magnitude diagram for a globular cluster. It's M3. And Sandage and Arp put together observations of a few more. And this is the classic textbook diagram that first, I think, appears in one of Sandage's papers, like a 4-page review paper in 1957, where he puts together all the color magnitude diagrams for M67, what's that, H and Chi Persei, and then here's M3 in here as an evolved population. And these guys down here, that's Roger Taylor, Martin Schwarzschild, Fred Hoyle, they were working on stellar evolution models to actually put together an explanation for why stars were evolving the way that we see there, trying to explain why there was a red giant branch. which actually still seems to be something that comes up. It's not entirely clear, I think, that people understand why stars turn into red giants. It's got something to do with entropy, but there doesn't seem to be a necessarily satisfying explanation, although we can model it perfectly. Metal-poor stars. Around about the 1950s was when people started to realize that not everything was solar abundance. This is a paper by Chamberlain and Aller that analyzed, well, it says A-type subdwarfs, high-velocity stars. There's HD 19445 and HD 140283, which we now know are metal-poor stars. I think one of the, they did a classic spectroscopic, what do you call it, curve of growth analysis of the spectra, and they found that they couldn't explain the spectra using solar metallicities. And they actually downplayed that in the paper because you can't see it, but down here, the one possibly undesirable factor in our interpretation is the prediction of abnormally small amounts of calcium and iron. And if you look up a paper, there's a review, I think Lawrence Aller's annual reviews article, he talks about how they actually, they found a lower abundance than they published, but they were really nervous about publishing such a low abundance for these stars. So they kind of backed off in the paper. But this was the first indication that there were actually metal-poor stars there. And Nancy Roman took this a bit further and showed that the high-velocity stars tended to have, they were F-type spectra if you looked at the hydrogen lines, but they were much earlier type if you looked at the metal lines or the absence of metal lines in there. So this was starting to understand, to recognize that the fact that these objects looked so peculiar, so blue, was the lack of line blanketing due to the lack of metal lines in there. And Nancy Roman is, I think that's orbiting Astronomical Observatory 1, because she actually moved into NASA in the early years of its existence and really was a major contributor to the big science emphasis within NASA at the moment. And they've actually named a fellowship after her for technology work, which is very well deserved. Okay, and then actually making elements. Burbage, Fowler and Hoyle, B squared FH, was published in 1957. And that was the first, really the fundamental paper describing how stellar nucleosynthesis transforms hydrogen and helium into heavier elements. It says what this. Experimental and observational evidence has continued to accumulate in recent years in support of the theory that the elements have been and are still being synthesized in stars. Since the appearance of a new and remarkable analysis by Swiss and Uri of the abundances of the elements, we have found it possible to explain in a general way the abundances of practically all the isotopes of the elements from hydrogen through uranium by synthesis in stars and supernovae. So again, that was a pretty fundamental paper. So Margaret Burbage, Jeff Burbage, Willie Fowler, and Fred Hoyle. I think that was at Willie Fowler's 60th birthday party in Cambridge. It's amazing how many parties happen in Cambridge. But they're not having one for Eglin, Lyndon, Bell, and Sandage. Okay, 1957, the Vatican Conference. That was another fundamental step in understanding what the galaxy looks like. All of the people who were movers and shakers in the field, Bada, Fowler, Hoyle, Morgan, Oort, Salpeter, Sandage, Stromgren, they all went to the Vatican in 1957. And the names escape me where it is, but basically they discussed stellar populations, whether they existed, what their properties were. And Oort put together this table that I'm not going to go through, but basically splits up things into disk, population to intermediate population, bulge, and quantifies what the observations were seeing in terms of the disparity of stellar properties within the Milky Way. And in fact, I think this year there is a 55th anniversary conference for this scheduled in July. I forget where exactly, maybe in Holland. There is one interesting thing I want to point out. There's the picture there. It's a remarkably undiverse group. This is when white males ran science. There is one woman in the picture. There are no people, I think, of any kind of color, but there's one woman. But then you look and you see that position Z is, in fact, Madame V. Preobrazhensky, chef du secretariat. So, anyway, I pass on. So, what was happening, and so in terms of the halo at that time, Sandage and Egan were working together looking at subdwarfs in the field. They took the first parallaxes. Egan at the time was at the Royal Observatory in England, at Herstmonceux Castle, which is why this paper was communicated by the Astronomer Royal. In those days, you weren't trusted to submit your own papers. You gave it to the guy in charge, and it always was he, decided whether to send it in or not. So this is a plot of absolute visual magnitude against B minus V, and various subdwarf stars that clearly lie below. And this is the Hyades main sequence. So it became clear from these parallax measurements that subdwarfs, metal poor, as they became to understand, metal poor stars lay below the main sequence. They were faint for their color. In the same way, this is a two-color diagram, U minus B, B minus V, classic diagram. This is the Hyades sequence. Subdwarfs also sat above this, the Hyades sequence in this diagram. They were bluer in U minus B than one would expect based on the B minus V. So spectroscopy showed that, the spectroscopy that Nancy Roman had done and others showed that this was metal line blanketing. There were fewer metals in the subdwarf stars, so there was less blanketing in the ultraviolet wavelengths, so more light got out through the U band, so they were brighter in U minus B. Sandage and Egan took this and turned it into a metallicity indicator. Well, actually two things, both a metallicity indicator and a luminosity indicator. They put together this description of, I guess, the first real photometric index, delta U minus B, which is the U minus B excess, the height that something fell above the Hyades sequence. And they basically, one thing you can see here is that this is not, the separation between these two lines, the sort of the upper, this is the most that a star would get above the Hyades sequence, the blanketing line they called it. That's not constant, so they had some correction factors. Essentially what you did was to measure B minus V and U minus V for an object, stick it down there, measure the distance above the Hyades sequence, and then apply a correction factor that scaled things, so that you had one index that referred to a wide range of temperatures. And that index they used then to calibrate the subluminosity of the object. So essentially they're measuring the ultraviolet excess, and they're saying the more metal poor a star is, the further below the main sequence it falls. So the paper itself. It's based on only data for only 221 stars, 108 nearby stars, and then 113 high velocity stars. That came, both of these came from some samples that Egan had been working on. All of the stars had parallax, proper motion, radial velocity, so that meant you know the space motions for those objects. What Lyndon Bell's contribution to the paper really was to put together a model galactic potential for the Milky Way. Then you can take the space motions that you have locally, put it into that potential, and measure the orbit. And the crucial part of the paper was looking at how those orbits changed as you changed the potential of the galaxy. So this is just the basic tools. This is it's essentially the description of the model. It's a rotation curve, 0 to 15, radius from the galactic center, 0 to 15 kiloparsecs, and then the rotation velocity. And they're tied to the Leiden 21 centimeter measurements of galactic rotation. Not tied terribly tightly, but at least they're in the ballpark. So it's a very simple model. It's axisymmetric, and then in the first calculations they made, they had a static potential. They derived the orbits. They parameterized it using the angular momentum, and then an eccentricity, which was basically the maximum distance from the galactic center minus the minimum distance divided by the sum of the maximum and minimum. So it's not a true eccentricity, but it's a way of measuring how elliptical the orbit is. And then they also measured the velocity perpendicular to the plane, z. So for a static potential, this is the kind of orbits that they got. They're unclosed, but essentially they are static. They have the same eccentricity, the same angular momentum, the same height above the plane throughout. The big step in this paper was to say what happens if you change the potential, and in particular what happens if you make it a rapidly varying potential. So this is obviously a step towards violent relaxation, because in violent relaxation you are changing the potential in a rapid fashion. What they found was that, and probably I should say what Lyndon Bell found, was that the changing the potential in a rapid fashion meant that the eccentricity changed, such that the systems became more eccentric. Angular momentum was conserved. Okay, so that's what the model showed. Then what they did was to take the stars in their sample. This is the U minus B excess, so this is basically metallicity. Solar type stars here, these are the solar neighborhood stars, and then the metal poor stars at high U minus B are from the high velocity sample. So there's a clear correlation here between, I should say, this is eccentricity, and this is metallicity. So they found a clear concentration between, a clear correlation between eccentricity and metallicity, in the sense that the metal-rich stars were on low eccentricity orbits, and the metal-poor stars were on high eccentricity orbits. So there's a couple of things that have been pointed out. One of the things is that the way that they constructed their sample, I mean, if you remember back, I said that the halo is very low density locally. So if you take 1 in 200 stars, if you get a sample of 100 stars in the nearby star sample, you're not going to pick out halo stars there. You're also not, if there are halo stars that have very low space motions, they're not going to appear in the sample at all because they won't be in the high velocity sample. So you could say there might be a selection effect such that metal poor stars in circular orbits wouldn't get into this picture. I mean, we know now that's not really a problem. There aren't many halo stars in circular orbits. The other thing that they actually pointed out in the paper themselves is that the junction, they could very well be underrepresented here because of the fact that they're combining two very distinct catalogues. These stars may not have entered into either catalogue. But the crucial step that they took in the paper was to say these metal poor stars, these ultraviolet excess stars that are high velocity stars actually have similar photometric characteristics to the stars in the globular clusters that Sandage had been looking at. So they drew the connection saying that metal poor means old. So then taking that big step, they said that the correlation between ultraviolet excess and eccentricity was actually a correlation between age and eccentricity. Old stars were in highly eccentric orbits. So I guess, yes, and those orbits, so in order to get stars onto orbits which go to large distances above the plane, they have to be born in clouds that are either at that height or of sufficient velocity to get to that height. So they concluded that these observations could be explained by having the subdwarfs form within a rapidly changing potential due to the rapid initial collapse of the galaxy. So that was their model for forming a galaxy. You have a collection of gas clouds that's collapsing very quickly and forming stars within a potential well. This plot here is just showing ultraviolet excess against the W velocity, which is the velocity perpendicular to the plane. So again, the metal poor stars, the old stars, have the large velocities that can take them to very large distances above the plane. This is 1 kiloparsec, 5 kiloparsecs. And that's the nub of the paper, that the galaxy formed as a giant system of collapsing gas. So where does it stand now? A complication came in somewhat later. Leonard Searle and Bob Zinn put together an extensive set of observations of globular clusters. And they found an interesting thing about the globular clusters, that they could be, you saw that they were separated into two groups based on metallicity. They found that looking at the globular clusters in near the center of the galaxy, they had remarkably homogeneous appearance. They tended to be more metal rich, but they tended to show the same characteristics. In the outer part of the galaxy, they found that globular clusters with the same abundance had very different morphologies. In particular, they had what's become known as the second parameter effect. The two clusters, M2, NGC 7006, with the same metallicity, have very different horizontal branches. So the horizontal branch for 7006 is very stubby. For M2, you have this extended blue horizontal branch. They parameterized this. This is the parameter R, which is the number of blue stars divided by the total number of stars in the horizontal branch. So 1 means that you're dominated by blue horizontal branch stars. 0 means that you don't have any. And I guess this is plotted against metallicity. So the big wodge of points here at the same metallicity says that you have this range of horizontal branch properties. They hypothesized that the reason that conditions were so diverse in the outer part of the galaxy was that the galaxy in the halo of the galaxy there was forming by accreting lots of satellites. That you had diverse conditions because they were coming from diverse places. Now Sandage, with his usual aplomb, described that as well. This was just Egan, Lindebell, and Sandage with a bit of noise on the outside. But it's an interesting new concept that Zinn took further by splitting things into the disk clusters and halo clusters. So this is the metal poor, these are the metal poor clusters, these are the metal rich clusters, this is the galaxy. So one can see that the metal rich clusters are much more centrally concentrated. And here you're looking at metallicity against number of objects, and so this is the same diagram that I showed from Bill Harris's paper. And then metallicity against height above the plane. The metal rich clusters are all concentrated at small heights above the plane and at relatively rich metallicities. So this was another thing to put into the mix. Another thing that's come into the mix recently, which also looks at accretion, is the lambda CDM simulations that are being carried out. So taking models of the universe and putting constraints on the power spectrum of the initial density fluctuations. Fluctuations. The lambda CDM models predict strongly hierarchical structure. So you have a few large objects and lots of small objects. And they predict that within the dark matter potentials that will form spiral galaxies, you should accrete a lot of small satellite systems. Now you probably know there is the satellite problem, that we don't actually see as many baryonic satellites as are predicted by the lambda CDM simulations. But there are possibilities they could exist as ultra-faint dwarf galaxies. There could be satellites there that are only dark matter, that we don't actually see any baryonic matter attached to them. But again, you're talking about accretion as a means of forming the galactic halo rather than a single collapsing system. And we do actually know that the Milky Way is accreting a galaxy. I mean, this is the Sagittarius dwarf. This is the discovery diagram that led to finding the Sagittarius dwarf. Rodrigo Ibata, Jerry Gilmore, and Mike Irwin were doing a survey towards the galactic bulge, basically wanting to look at bulge metallicities. So they took a multi-fiber spectrograph and they put a whole bunch of stars on on the fibers. And they got velocities, and they got colors. And they saw this weird thing in the diagram, that there wasn't just a dispersion of velocities. There was a consistent line of objects at the same velocity. They followed up on that. I think mainly Rodrigo and Mike Irwin followed up on that. And basically, these are all stars that are members of the Sagittarius dwarf. They have a low velocity dispersion because they're actually in another galaxy that's passing through the Milky Way. So this is one of these great serendipitous discoveries, that you go out there trying to measure the metallicity of the bulge and you find that we're actually accreting a dwarf satellite. And since then, there's been an awful lot of work that's been done on that system. There are at least 3 globulars, M54, Tarzan 7, and maybe Tarzan 6 as well, that are Sagittarius members. M54 might be the core of the Sagittarius dwarf. And M giants, the path of Sagittarius, it's left debris all around the Milky Way, and you can trace that path with things like M giants. Katherine Johnson in particular has put together some remarkable models that show, so here's the Milky Way. This is the debris that Sagittarius has left behind it or ejected in front of it as it's being swallowed by the Milky Way. So satellite accretion certainly happens. And then there's this plot from the Sloan Digital Sky Survey, where I believe this stream here, I think, so this is just surface density of stars on the sky. This stream here, I think, is the Sagittarius stream. Then there's a thin stream up here that you probably can't see, but that are attributed to other satellites that may have been accreted by the Milky Way. So there's a bit of cannibalism going on out there, and certainly things are being accreted. Yeah, and there's this thing called the Canis Major dwarf galaxy, which may or may not exist. There's basically an excess of stars in Canis Major. So there's accretion going on. Does that mean that satellite galaxies built the halo? Well, possibly it does, but it's certainly not satellites that are like the current satellites that we know about. This is a diagram from Eileen Tolstoy's work, which plots the calcium to Fe, so alpha abundance element, alpha abundance against Fe over H for the halo, the black dots, and then for a bunch of satellite systems, including the Sagittarius dwarf. And essentially, in most cases, the current dwarfs, so these are dwarf spheroidal galaxies that are still existing around the Milky Way at the moment, they don't have the same alpha enhancement as the halo does. That doesn't mean that satellites didn't build the Milky Way halo. It does mean that if they did, they're not identical to the satellites that we have now. So an interesting piece in the puzzle. And now we come to globular clusters. So this is the classic picture of a globular cluster. It's a single coeval burst of star formation. Everything's got the same metallicity. Everything's got the same helium abundance. And they all formed together and lived happily ever after until they got stripped off. And that picture turns out to be almost completely wrong for just about every globular that we know. And that's, I think, one of the most remarkable discoveries of the last 5 years or so. It started, the first sort of fly in the ointment, and it's been in there for some time, was Omega Cen, which is the biggest globular cluster. I mean, for a long time, it has a range of metallicities. It's been suggested for a long time. Ken Freeman back in 1973 suggested it might be the core of a dwarf galaxy, just because it was clearly a multiple stellar population, even back then. There's a range of cyanogen and CH abundances on the red giant for the red giant stars. It's clearly the abundances of the main sequence stars go from -1 to -1.9. But for a long time, it was the only one. It was peculiar. There were abundance anomalies that were found by people like Nick Suntsev, Bob Kraft, John Norris in globular clusters. If you look at the giant branch stars, you could see that, again, this dichotomy between strong Cn and strong Ch would crop up in quite a number of clusters. And there was also an anti-correlation between oxygen and sodium abundances that came out of work by Judy Cohen and Ruth Peterson in the late 70s and early 80s. But there was a big argument about, because this was all in giant branch stars, you had this argument about, was it nature or nurture? Was it something that was intrinsic to the red giants themselves when they formed, or was it something that happened afterwards? Because red giants have they have giant convective envelopes, so they can dredge up material from the core and perhaps change their own abundance. So this argument raged on for, well, it didn't actually rage. They were all nice people, mainly. So it simmered for a number of years. And then HST has really made the difference here. This is Omega Cen. It's not just got two populations. There are 4 or 5 distinct populations in Omega Cen, with differences, with age differences, with abundance differences. And the reason that you can say that is because with HST, and I don't just say that because I work there, but with HST you can get phenomenal precision, and you can actually split off things. You can start to see things that, I mean, there's one subgiant branch, there's another subgiant branch, there's another one. They're color-coded down here. This is an amazingly complex system. And one of the things going on is that down here, this blue sequence, the only way you can explain that is by having a high helium abundance. You have to crank up the helium abundance to 0.38. And I mean, there are some people in the audience, and amongst your participants here who know this better than I do, but essentially the way you do that is to very hot burning in a star, and you transform a lot of hydrogen to helium. So this cluster needed to have undergone multiple episodes of star formation. That means it had to be sufficiently massive to retain gas. You know, the classic picture of a globular cluster was something that formed stars once. You had a giant starburst, and that starburst blew out all of the gas. And then you couldn't have any more star formation. You couldn't have anything after that because there was no gas. Well, now we see that in Omega Cen, you certainly had to retain gas long enough for it to be polluted by the first generation, and then the second and third, in this case, the fourth generation of stars. I mean, I think this is really, it's one of the most remarkable changes in how we think about a common object in the galaxy, if globular clusters don't mind being referred to as common objects, certainly in my lifetime. And now the other thing is that there are multiple populations cropping up in just about every globular you look at. I mean, first of all, Giampaolo Piotto is kind of the king of multiple populations. And then, so every paper has an Italian as the first author. But that's okay. This is NGC 2808, which is another massive cluster. But NGC 6397 is the archetypal metal poor cluster. It's about minus 1.8. It's, I guess, the second closest globular cluster. Even it has a bimodal sequence in there. So that clearly, globular clusters were not the simple single burst things that we thought even a matter of 5 or 10 years ago. Yep.
And the last sentence in your previous slide was, are any globular in the globular simple system? Has any been studied deeply enough and concluded to be a simple population?
I don't know of one where it's unequivocal yet. I mean, this one would have been my kind of. The thing is, you have to get fairly deep observations, even with HST, to get far enough down there to see if there's a splitting on the main sequence. So not all, and the focus initially was on the massive clusters because those were the ones that were always showing up. But do you want, yeah.
There is also one thing related to the splitting in photometry, that from spectroscopy you can see that giant branch and internal star are spread in light elements basically in every globular cluster, which are related to the multiple population. So I think for now, in each globular cluster where we have searched for spread in light elements, we have found them. So it's possible that every globular cluster has at least 2 populations of stars.
Yeah. So big change. One of there were a lot of or at least some of the HST data came from a large program I was involved in. Atta Sarajadini was the PI, and we got data for 64 globular clusters, just 2 colors, and just a couple of orbits of each. One thing that we used that for, to kind of drag it back to something vaguely relevant to the topic here, was to look at the mass function and to look at mass segregation. So this plot here, this is the mass function for a bunch of globulars that we observed. The main thing that came out of our work was that there was a strong correlation between the slope of the mass function, if you parameterize it with a power law, and the mass of the cluster. Basically, the higher mass clusters had, and I'm going to get this right, steeper mass functions in the sense that they had more low mass stars. So the lower mass, the lower the total mass of the globular cluster system, the fewer low mass stars it had in relation to stars near the turnoff. And the simplest way of explaining that is to say that it's all due to dynamical evolution. And these are things that are plunging out in and out of the galaxy every, I don't know, few times 10 to the 8 years. As they go through the disk, as they go through the bulge, they're going to have lots of gravitational interactions. All of these clusters show some indication of mass segregation. The low mass stars are the outside, they're the ones that are going to get pulled off. But the interesting thing is that there isn't any reason from these data to think that the globular cluster mass function was any different than the mass function that we see in the field. I mean, there's nothing in, all of the differences here are in the sense of going flatter than what we see in the field. So even down at abundances of -2, it looks like the initial mass function just does the same thing. And yep.
We had a paper a few weeks ago in AstroPH where we ran some Monte Carlo models with the same initial conditions, spanning a range of cluster masses, and evolved them for 10 gigayears, and then compared them to this sample and showed that indeed it is consistent with what you would expect.
Excellent.
From relaxation.
Good. Thank you very much. But what was the other thing I was going to say? Never mind. If it was important, it will come back, and it probably wasn't. But yes?
I should point out one thing that's from some theoretical work, is that if you start out with mass function that's steeper than canonical,
Mm-hmm.
The dearth of massive stars enables a more effective depletion of the low mass end, because every stellar mass has a tendency to eject stars of about 20% of their own mass. So if there are a lot of massive stars, these want to deplete stars that are not at the very low mass end.
Mm-hmm.
So by minimizing their number, the very low mass end will actually drop further, because the most massive stars are then not the dominant ejector set.
So basically, so you're saying that essentially there's a big insensitivity there that
Exactly.
backtracking.
Yes, so in that sense, it might be very hard to relate this directly to the IMF.
That's a good point. I think this was. I guess that this doesn't say that the IMF hasn't changed. What it does say is that globular clusters don't provide any evidence that it would have changed.
Yes.
And I mentioned this to Lyndon Bell when I saw him at one point, and he said, well, of course it didn't. If you look at my paper in 1976, the fragmentation only depends on the opacity to the 1/7 power, so clearly metallicity doesn't make a difference. So Donald just proved it. This is just one of my favorite clusters, NGC 6366. This is its mass function with that kind of notional power law driven through it. This is high mass. This is low mass. Essentially, this is flat in the sense of m to the 0. The dominant. This is like Taurus. The most frequent stars in this cluster are the stars near the turnoff, and then it gets fainter there. And this actually turns out to be an orbit where it goes through the galactic bulge with depressing regularity. So you can't actually say anything about the initial mass function from this, but it's kind of cute that it's done this badly. Okay. Star streams. We can actually see star streams for some globular clusters. This is PAL 5, and I have to actually look at where I stole this figure from. But these are tidal tails. PAL 5 is one of the most distant globular clusters, so it doesn't have very much of a background. But essentially, what you're seeing here are debris being stripped from the cluster itself. And NGC 1851, another globular, you can actually see a kind of halo of an NGC 1851 star stream diffusing round about it. Yes?
Can I be terribly annoying? Please tell me off if you feel the need. You call this tidal stripping, but in principle it is a different physical mechanism, because it is just the two-body relaxation that shoots out stars over a tidal boundary, whereas tidal stripping suggests that the tidal boundary decreases and therefore removes some outer layer of the stars.
Right, the tidal stripping would require something else to come and do the stripping.
Exactly.
Yeah.
Here it is just the presence of the boundary that
Yep.
the stars can be kicked out of by two-body relaxation.
Right, your not irritating comment is well received. No, that's true. That it's actually it's more of a diffusion process rather than an interaction process. But as an observer, I just call it tidal stripping. So binaries. How much time do I have left?
7 minutes.
Oh, okay. Good. So binaries. We can actually detect some binaries in globular clusters. There's a paper by Maloney for looking at the HST survey that we have. And he's done an excellent job of going through. And the only binaries you can detect in globular clusters are photometric systems. Nobody's yet done, I don't think we necessarily have the capabilities to do a full radial velocity survey for spectroscopic binaries. So the only way you can set constraints on binary, large scale constraints, is by looking at the main sequence, and binary stars will scatter up above the main sequence because there's 2 stars there instead of 1. So with that caveat that you're only looking, and that then sets the limit in terms of mass ratios. You can only get high mass ratio systems there. But Maloney has done an excellent job of going through and looking at the globular clusters in our sample. A whole bunch of corrections. I don't need to go through them here. But I think the main point is to say there's a range of binary fractions in the globular clusters. And in fact, the correlation is such that low luminosity clusters have higher binary fraction. And that, I think, is consistent with dynamical evolution. The binaries are going to sink towards the center of the cluster. The lower mass clusters are the ones that are subject to more stripping. So as you strip the outside of the cluster, you're preferentially taking away single stars. So the higher mass clusters manage to hang on to more of their single stars, which is why the binary fraction is less. This is a plot here. This is the absolute magnitude of the globular cluster, and this is the fraction of binaries in the system. And as you can see, it's only the actual measured fraction is only of the order of 5 to 10%. But with the big caveat that clearly we know we're only looking at the high mass ratio binaries in there. Doing a multi-object spectroscopic series of observations. Yep.
I don't know if the ejection rate as a function of radius within a globular cluster actually peaks towards the outskirts, because the interactions are stronger in the center, so in principle the velocities that the stars are receiving from there should enable them to escape as well, even though it's usually successive.
Right. So this may be more an effect than of the external interactions, because there will be real tidal stripping episodes as you're going in and out of. So it's possible that that's the more important effect here.
Indeed, and another thing that might happen is because these clusters are lower mass, they go into core collapse earlier, which increases the density, which could suggest that these binaries are dynamically created.
No, there's way too many. Way too many binaries for that.
But anyway.
That's a problem then,
Why?
because low mass clusters do go into core collapse from
Right.
So that wouldn't lead to the destruction of these binaries?
He's talking about primordial percentages that may even hold off the core collapse.
Fair enough.
So clusters are relevant. Okay, I think I've only got a couple more. Cluster ages.
Sorry, Neil, another question?
Yep, sure, sorry.
If you have more stars, your standard densities are higher, then you can't have the wide binaries. So,
Right.
well, because
Yeah, I agree, yes. Because
could that be a reason for having less binaries in denser systems?
I don't know. It's a good point. I think it would. I don't know that we've actually looked at how the density varies and how much that would constrain things. But yeah, obviously you're right. If you've got a higher density in there, but then on the other hand, if you've got the core collapse in the lower mass clusters, maybe the densities are actually more comparable.
Well, I think if you add Bob's remark, this kind of gives a consistent picture.
Okay. So there's not really core collapse because there's enough binaries, but there's not too many. Okay. Let me just skip over the age. The ages are not necessarily terribly relevant, except to say that most of the globular clusters tend to have the same age. Measuring relative ages for globular clusters is relatively straightforward. Measuring absolute ages for globular clusters is absolutely difficult. But if you look at the comparison, then most clusters actually have roughly the same age, but there's a few clusters, mainly at higher metallicity, that appear to have younger ages. So, and I'm going to skip on. Come on, skip. Thank you. Skip further. Thank you. So for the absolute ages, Hipparcos had a big effect. Hipparcos did things differently from Gaia. Hipparcos in the early 1980s, they actually put out a call for people to put in a list of objects to observe. So I went through the Gickless catalogue and pulled out as many proper motion stars as possible and just sent it off there. It was about 2,000 stars. Bernard Padgel told me that at the meeting there was some objections from some people that they didn't want Hipparcos to observe these stars because they might move. They just wanted to observe reference frame stars. However, they did actually observe them. And then Hipparcos was launched, and in 1996 I got the result of my observing request, submitted 13 years earlier. So what I did was to take the subdwarfs in there and just for fun plot them up against the color magnitude diagrams of some globular clusters. And it turned out the distances that I got from the Hipparcos parallaxes for the subdwarfs were different by about, I forget, 3 or 4 tenths of a magnitude with respect to the standard values. And that made a big difference then, because the standard values and the standard models were saying that the globular clusters were 15 billion years old. And we knew that from WMAP that the universe was only 13.5 billion years old. Actually, it wasn't WMAP yet, but it was a real problem for the Big Bang. So I got all excited. But then Adam Rees went and discovered dark energy, which meant that distances in h naughts didn't actually count for anything anymore. But nonetheless, the Hipparcos data for the local stars gave a reference point for measuring distances to the globular clusters. And then you got a good measurement of the turn-off luminosity. And from that turn-off luminosity, you could estimate ages. And this has been done more recently. This is something where Gaia is, again, going to come in and really add lots more calibrating points nearby to get much better distances out there. And when you look at the ages, the consensus age now is about 11 to 13 billion years, which is completely consistent with everything we know about the Big Bang. Atis Arjadini has a recent paper where he gets 11.6 plus 1.4 minus 1.1 as the age. And in fact, this appears to be consistent with the age that is being estimated for halo stars as well. This is a kind of complicated diagram. It's metallicity against G minus R color for halo stars. And this is a kind of turn-off for the halo that's being placed in there. Okay. So formation of globular clusters. So we have this picture now where we know that 2% of the mass of the galactic halo is in globular clusters. We know that they have multiple populations. We know that in order to have multiple populations, they need to be much more massive in the past. And the models suggest that they needed to be somewhere between 10 and 25 times more massive in the past than they are now. We know that the globular clusters are on these plunging orbits. So the bottom line here is that, and Raphael Gratton has a series of papers looking at this, and various other people are looking at it as well. But the argument is that maybe the globular clusters actually formed the galactic halo. The globular clusters are the remnants of the initial clouds, of the initial star formation that actually produced the halo as a whole. Every halo star formed, or not every halo star, most halo stars formed in globular clusters, which then got stripped out since then. So, actually, I guess the epoch of formation, just to put this in a cosmological concept, the old clusters are forming at redshifts between 4 and 8. The more recent clusters, the accreted clusters, are forming at redshifts 2 to 4. So that's actually most of the halo formation seems to be going on here. This is redshift against star formation rate, the classic Madao plot. So most of the halo formation seems to be going on just at the start of the maximum star formation. And just for fun, I pulled out, you can't see them here terribly well, but these are redshift 6 galaxies. You can't see globular clusters forming there, but presumably that's where they are forming. So summary. Everybody should read ELS because it really did change the way that we think about the galaxy. Its concepts are still very valid and maybe coming back into vogue again. Dwarf galaxies are merging with the Milky Way. They may not contribute much to the fact to the halo, but there clearly are some mergers going on nowadays. Globular clusters are not simple systems, and it's possible that Sandige's notion of ELS plus noise as how the galaxy formed is just globular clusters plus a bit of noise. So, outstanding questions. You can read them from there. So, thank you. Yep.
So this may be a very naive question, but I mean, you have multiple populations in globular clusters. As far as I know, maybe I'm mistaken, but they're not all rotating at the same. I mean, they're
Right.
And you have streams. Couldn't they just be tiny galaxies accreted, and that's the remnants you see? Why is that not a possibility?
I think that is it. I think that the globular clusters, I think what we're seeing now is that the globular clusters really are galaxy remnants. I mean, in some ways, it's almost semantics. That we've called these as, Mike?
What about dark matter halos?
I don't know. What about dark matter halos?
They're absent.
Yep. But, well, maybe,
Distinction.
do they have to have dark matter halos to be galaxies?
That's the idea of bottom-up galaxy formation.
Right.
The first halos must have formed before reionization, and baryons couldn't do that.
But we have observational evidence that globular clusters were, at least some of them had masses comparable to galaxies.
Do we?
Well, I think omega Cen, you have to crank it up. It's going to be comparable to a dwarf galaxy. And it doesn't have a dark matter halo. So I would say on the observational side, we go then to the theory and say, how do you explain losing a dark matter halo? So I think,
Well, perhaps because it isn't a galaxy.
yeah, I don't know whether we're just playing with words there.
Well,
So but I mean, it's entirely possible that you could have a complex system being absorbed that isn't a galaxy. But I mean, that's an interesting question. I'm not going to pretend that I know the answer to it. But the fact is that we're seeing that things are much more complicated in the globular cluster world than we thought.
just because of the multiple population.
Yeah. Yeah, but just because, and in fact, this really is what you were talking about this morning, that when the gas goes away, the system is going to disperse unless it's got sufficient mass in of its own right. And here you've got to keep the thing in place long enough with some gas to pollute the gas and form a second generation of stars.
But this is considering that, this is assuming that globular clusters form in total isolation. And of course, we do not see any globular clusters form in the nearby universe. So we don't have a clue. It might well be that there were environmental effects like the compact, high redshift dwarf galaxies in which globular clusters may have formed that helped retain gas, which may have been accreted at a later stage, high ambient pressure. I can imagine a whole lot of things that would lead to multiple populations in a high redshift environment.
Okay,
Even
but
at masses close to the presently observed one.
I'm not going to argue with you. I'm just saying you now have to imagine that, which is a good thing.
So I'm not going to argue either. I'm just
Yeah.
trying to say that I don't think it is. It may be an indication, but it's definitely not evidence that globular clusters were 10 to 100 times more massive or were galaxies.
I do. Yeah. Good. Yeah. Next.
So I heard this talk about the multiple sequences problem by Allison Sills, and from the talk I got the impression that for almost all of them there are two sequences and no more and no less. Obviously omega Cen is an exception, but maybe you can explain that because it's definitely, or it's likely to be the core of the galaxy. So besides that one, almost all of them.
There are a few others, NGC 2808. The most massive globular clusters now have the most populations. But yes, I think,
So,
I believe.
so I was wondering if that's still true. And she had some model for how it may come to be where you have a first round of star formation, then after stars begin evolving, there's a second round of star formation, which may be enriched by the by material from ejected by the first round of
Okay, yeah, I think, yeah.
formation.
I think that sounds, that's basically, as far my understanding is that most of the clusters that have multiples, it's multiples where multiple is 2. So yeah, I think that's right. Yes?
I wonder if there are any systematics in these multiple populations in the time span between the episodes of the star formation.
So I believe that in most cases, their age difference is small or non-existent. In most cases, it looks like it's an abundance effect, either heavy metals or helium. I think omega Cen is probably the only one that stands out where there are these different turn-offs that do suggest quite a range in age. Maybe 1851 as well. But in most cases, I think it looks like they're pretty close together in time. Well, it's exciting because it's a rapidly evolving field. Bob, did you want to?
And much more a mundane question. I lost track of your story of where the disk metal-rich collaborations came from.
They were probably the most metal-rich ones to form. I don't think we necessarily have a good picture for that. At least I don't. So, Kathy?
Common question. Comment is, I think core collapse only involves function of the mass of the system, so I don't think you have to worry about annihilating all the binaries in core collapse. And the question was, this factor 25, that's just a binding energy argument, isn't it?
Yes.
Okay.
I think you were quoting some numbers similar to that? No, somebody was. Somebody who said it. Never mind. I think 10 to 25 is, no, not you. Never mind. I imagined it.
You just contain gas at a certain temperature.
Yeah.
Yeah.
Okay. Let's stand up, stretch, and then we can have the next fantasy.